Sai Ram. We welcome you all to the post-lunch session of the day one of the International Symposium on Chemistry for a Sustainable Future Bridging Science and Society. The first speaker for the afternoon session is Professor Vinayak Sinha, Department of Earth and Environmental Sciences, IISER Mohali, Punjab. Professor Vinayak Sinha will be addressing us on the topic Aligning Clean Air and Climate Action, Selected Insights from a Decade of Atmospheric Chemistry Research over South Asia to foster transdisciplinary research. We request our student Ashish Chetri to introduce and invite Professor Vinayak Sinha. Sai Ram.
Shri Om Shri Sai Ram. Invoking Bhagavan's divine blessing. Good afternoon and Sai Ram to one and all present here. It is my great honor to introduce the speaker for the session, Professor Vinayak Sinha sir, a distinguished scientist whose work has significantly advanced our understanding of atmospheric chemistry and its impact on climate and air quality. Professor Sinha is currently a faculty member at the Indian Institute of Science, Education and Research, IISER Mohali. Sir has done his BSc and MSc degree from the Sri Sathya Sai Institute of Higher Learning. Then he went on to complete his MTech in Analytical Chemistry from IIT Delhi and a PhD from the prestigious Max Planck Institute for Chemistry in Mainz, Germany. An analytical and atmospheric chemist of global repute, Professor Sinha's expertise span several critical areas, including source apportionment, ozone and hydroxyl radical chemistry, molecular chemical fingerprinting of air pollution sources, and volatile organic compounds VOC analysis. He has the unique distinction of establishing India's first proton transfer reaction mass spectrometry lab, which has been operational since 2011. This pioneering facility has enabled continuous high sensitivity atmospheric composition and meteorological measurements for over 100 species, including VOCs at parts per trillion sensitivity. A prolific research, Professor Sinha has authored over 132 scientific publications, including 82 peer-reviewed journal articles with the impressive H index of 38 and nearly 4,000 citations. Beyond his research, he serves as an expert member of international bodies such as World Meteorological Organization, Environment Pollution, and Atmospheric Chemistry Scientific Steering Committee, and the International Commission on Atmospheric Chemistry and Global Pollution. Today, we are privileged to hear from a scientist whose work bridges fundamental science and real-world solution. Today, Sir is addressing us on the topic Aligning Clean Air and Climate Action, Selected Insights from a Decade of Atmospheric Chemistry Research over South Asia to foster transdisciplinary research. Please join me in warmly welcoming Professor Vinayak Sinha, sir.
Thank you, brother, for that. Shri Sai Ram, for that kind introduction. Um, am I audible to the last person in the audience? Okay. I am known to go very high pitched in the middle. So if it's not sounding very good to your ears, just raise your hand at the back and I'll tone down a bit. So, yeah. Sai Ram, dear sisters, brothers, it's really a great privilege and honor to be here at my alma mater, the place we all consider our true home, thanks to our Divine Mother and Father. So, just to show you, like Professor Venkat Krishnan had shown, this is the place where we work. This is actually the ISER Mohali campus. It's just a few kilometers away from the foothills of the Himalayas, which you can see on a clean day. So extra incentive to keep the air clean. And most of the instruments and data I'd be showing you today are actually acquired using instruments that are there housed in the Central Analytical Facility building. Right. So, yeah. Just gratitude again to our beloved Divine Mother, thanks to whom we all are here today, and for everything that has been possible for this person to achieve. Sai Ram. So, the outline of today's talk, because it's a general audience and lot of undergraduate students, is in such a way that first we'll try and establish the connection between the chemical composition of the atmosphere, so what essentially is there in the air, which molecules are present, how that in turn affects the climate and the air quality that we all have to experience on this planet, and what are some of the current key challenges when we look at it from a global perspective and more so from a South Asian and India relevant picture. Then I'll be going and showcasing, I've deliberately kept it focused on just one of the topics that our research group has been very active in, which is developing applications using molecules that we can measure in the air to do quantitative source apportionment and tell people, okay, if there is a particular molecule out there in the air, how much of it is from this particular source, and in a manner that is not qualitative but also quantitative. So you'll see that that actually unravels a great world of molecules that even I, who was trained as a chemist, found that atmospheric chemistry really is something that we perhaps only scratch on the surface in our country, and I'm hoping that such a talk would help all of us to see and invest more efforts on this, because this is really one of the key disciplines that's required to ensure sustainability with the environment. And of course, I'll be doing that with some concrete examples that thanks to Bhagwan's grace, the research group in ISER Mohali with the students, many of them of whom have done their BSc and MSc in Puttaparthi in our own institute, then subsequently joined for a PhD program at ISER and helped carry forward this work. So you can kind of see Bhagwan's divine plan there. Right. So let's start with some very basic thing. We all know and we've seen these sources around us, right? They are human-induced sources, which we call anthropogenic sources, that emit molecules whenever we operate them. These wouldn't be there but for us being on the planet. And since the year 1850, which is kind of taken as the baseline year for the onset of the industrial era, these have been growing in intensity and in magnitude, right? So literally, we put in molecules from these anthropogenic sources. But we should also remember that nature has its own sources by which it was doing very, very elegant atmospheric chemistry, which actually ends up producing less of secondary pollutants like particulate matter, which you may have read about in the news, or ozone. And these sources also are quite significant. In fact, just to interest you, the greenhouse gas warming, if we had had no atmosphere, or even if we had an atmosphere with no greenhouse gases in it, then the average temperature of the Earth would have been a freezing minus 18 degrees Celsius, 255. And so that has nothing to do with human beings. Thanks to the presence of the greenhouse gases like methane, carbon dioxide, which the natural contributions, we have an average temperature for the last 100 years or so that has been pretty stable at around 288 Kelvin or so. So, or 13 degrees Celsius, right? So that makes it habitable. And the only problem is that we've been pumping into the air for our energy requirements. We dig up the fossil fuel, the coal, the oil, we all know this, you've studied in school too, and then we burn it in a variety of different combustion processes. And once these molecules end up in the atmosphere, then that's where they act like a reactant mixture. So you can view the entire atmosphere as like a chemical reactor in which now you've added more molecules. And here, my group specializes in one particular type of molecules that are very useful. They are called volatile organic compounds. So they primarily exist as gases. And these traditionally exclude carbon dioxide and carbon monoxide from it, because the simplest member of this group is actually methane, which is also a greenhouse gas. So once in the air through OH radical initiated oxidation, the OH radical acts like the soap of the atmosphere, you know, like a detergent. Like every day we take bath. Similarly, this radical, which is formed in the daytime primarily from ozone and sunlight and some water vapor, nature's beautiful chemistry, this converts the initial molecule into a form that is more easily removed from the atmosphere. So you don't need to be a chemist to appreciate what's happening here. You may have an initial molecule, let's take benzene. We've all heard about benzene today, right? When it gets oxidized, it gets converted to something like an oxygenated volatile organic compound like phenol or cresol. Now, phenol is more water soluble than benzene, as you would remember from your high school chemistry. Not only that, during this oxidation, we keep adding oxygen atoms, which increases the molecular weight of the molecule, the initial molecule that was emitted, and that makes it less volatile in general. And as a result of that, then when you have also nitrogen oxides in the troposphere, the lowest part of the atmosphere where we live and breathe, it can form what we call ozone. This ozone is very different from the good ozone between 20 and 50 kilometers above our heads, which is the stratospheric ozone. We want that to remain as it is because it shields us from the harmful UV radiation. But this ozone down here, pre-industrial levels of this were only about 30 ppb or less. And today, many cities, many continental regions, if not all, frequently experience ozone levels that are in exceedance of 100 ppb. And 40 ppb of ozone is enough to damage plants. 60 ppb ozone, if we breathe that continuously, is also very harmful for our lungs. You may have heard of COPD-related diseases because it's a pulmonary irritant. And then when we talk about the PM 2.5, which is basically aerosol particles that are dispersed in the carrier gas, 78% of the atmosphere is nitrogen. These particles also form a significant fraction of the particulate matter which we inhale. And how they contribute to that, this VOC oxidation, is through the formation of what we call secondary organic aerosols. So SOA really stands for that. And in all Indian cities, irrespective of the season, more than half of the PM 2.5 and PM1, which generally the general public thinks of it as only directly emitted pollution from your car exhaust or from your industrial activity, actually 50% or more in all seasons is made up of the secondary organic aerosol. So now if you want to bring down the ambient PM 2.5, how can you do that? Just by focusing on the primary emissions. You also need to worry about the chemistry and what toxic substances are formed as part of this. And of course, we know that in addition to the primary emitted carbon dioxide, there is a lot of secondary carbon dioxide that can come. It's much less in magnitude than the primary, of course, but it's still a significant contribution in certain city environments. And so just to give you an example of the amount of reactive material in terms of these molecules that we're talking about, India's population is, I think, more than 1.3 billion by now. If you give each person about 1 kilogram of potato and tell them, please stack it up, then you'll come up with about 1 teragram, right? 10 to the power 12 grams is 1 teragram. And here we're talking of a really, really large number. But you don't hear about this accumulating in the atmosphere like methane, like nitrous oxide, primarily because of this chemistry. But even though we can't measure these molecules directly, right, with our eyes, we can see the effects of these molecules in our everyday life. So this I don't need to explain for those of us who live here in this part of the world, and also in many other parts of the world, in fact. But also it may interest you to know that the clouds, which are responsible for rainfall, which cleans up the atmosphere, many of these emissions can go and sit into the clouds and change its radiative property. If you have black carbon, brown carbon, which are more absorbing in nature, then they can locally heat up the cloud and cause it to evaporate prematurely before it even gets a chance to rain out. So all in all, we do need to worry about all of this, and it involves a lot of interdisciplinary physics, chemistry, biology, mathematics. And this is really a great playground to look at sustainability because it affects the society directly. Okay, so these are just some numbers. This is the observed warming, because I wanted to sensitize our audience about climate today. That is about 1 degree if you look at it. So what is this? This is the decadal warm 2010 to 2019, about 20 years, right? Relative to 1850 to 1900, sort of considered the baseline years. So there's been an increase of 1 degree. Now, the Intergovernmental Panel on Climate Change, which by the way also won a Nobel Prize in 2007 for peace, they have, through the work of many scientists and leading academies of the world, come up with assessment reports every 4 or 5 years. And what they say is that most of this warming can be attributed to primarily, you can see, total human influence. And if you just take the natural one, people often talk about natural variability. Maybe the sun has dimmed a little, maybe there is volcanic eruption. So all of that is this minuscule number here. And so some components, they warm, and some components, they cool. And if we now look at the specific molecules per se, okay, I have to be here, then you can see that, of course, we have all heard about carbon dioxide. This is the single most important contributor. Nonetheless, there are several other molecules like methane, nitrous oxide, N2O. We often call it a laughing gas, not a laughing matter here, the CFCs, the halogenated gases. And the list goes on, along with the other aerosol components. And they have contributed, if you look at it, then they actually contribute, including ozone. Tropospheric ozone is also a greenhouse gas. In fact, the third most important. Collectively, they rival the impact of carbon dioxide on the Earth's planet. So really, and here's an incentive. You know, carbon dioxide, once you emit 100 molecules of it today, if you're just relying on the chemistry to remove it, it'll stick, about 67 of them will still be there for the next 100 years. Only 67 of those 100 would be removed after about 100 years. So it has a really long lifetime because it chemically doesn't react with anything. But methane, on the other hand, 10 years lifetime. So if we can bring down or control the emissions of these, we actually stand to gain the fastest in terms of winning climate co-benefits. Now, if we look at how the temperature scene looks like, you know, this is from a paper published in Journal of Geophysical Research Letters. And here you see, I hope you can recognize a map of largely South Asia, India. And what do you see? I'll walk you through it. You see the darker colors. So this is basically showing a temperature that is called the wet bulb temperature. Please let me explain this to you. We've all experienced that when the air is highly humid and hot, we experience much more discomfort than if the air were to be simply dry. So the wet bulb temperature is simply if you take an air parcel and manage to evaporate all the water vapor in it at constant pressure, then you come up with what is called the wet bulb temperature. And it's very important for human survivability because the way our body cools is through this evaporation process, right? If the air already holds the maximum amount of water vapor it can, then how will sweating and the consequent evaporation of the sweat help cool down the body temperature? Hence, the wet bulb temperature is always less than or equal to the actual maximum ambient temperature. And the alarming thing is that for human survivability, the wet bulb temperature should be below 35 degrees Celsius. This is not something that we atmospheric chemists say. This is something that epidemiologists have said. So please understand the implications of this. This means that all outdoor work, construction activity, farming, laborers, people who are not shielded and privileged like us in these rooms, right? All of them will not be able for extended hours in the very near future, even with the current 1.5 degrees Celsius warming. I mean, right now we are on track to absolutely miss this. But even with this, large parts of our country will be rendered inhospitable for outdoor work. And so, if this is not a wake-up call, I don't know what is. And when we talk about sustainability, I would also like, especially as Bhagwan's, people who have had the opportunity to listen to Bhagwan, ask ourselves what Mahatma Gandhi also said long ago. You must always understand what is the consequence of this on the most vulnerable, the people with the lowest access to protecting themselves in society. Okay, so also if we look at now just a specific molecule, ozone, this is surface ozone, the troposphere, the bad ozone so called. Okay, this region is supposed to be a global hotspot for that. So now, yeah, we can go on and on about more data, but I think we all get the drift by now that this is a really serious issue and on so many different levels. And in fact, this just tells that outdoor air pollution is going to exceed the mortality cause compared to a large number of factors that were the leading cause of mortality in the past decades. So we've covered now half of the talk. How am I doing with the time? Okay, great. So now we can look at real world examples. So one of the first things that I encountered when I started measuring here is, when I started after an MTech at IIT Delhi in the Department of Chemistry, and it was also sort of a Petrotech fellowship with the Department of Chemical Engineering, I kept applying to positions in Germany for a PhD, and I got a call from Max Planck Institute for Chemistry. I thought they'd be doing a lot of the traditional chemistry. Turns out that Max Planck Institute of Chemistry since the 1980s had completely shifted its focus to atmospheric chemistry. They had 3 divisions. And the 1995 Nobel Prize for Chemistry for understanding stratospheric ozone went to Professor Paul Crutzen, who actually was an emeritus director at the time when I had the good fortune by Bhagwan's grace to do a PhD there. And so why I'm mentioning this is because I went there and I thought, okay, I got a PhD position, thank you, Swami. I'll get about 1,000 euros, that's comfortable. It's like I'll get a PhD and also from a good place, and I can save some money and send it back home. Common things that most young people think at that stage. And then I thought, but what am I going to do research on? 78% of the air is nitrogen, it's inert, we use it as a carrier gas normally. And 21% is oxygen. It doesn't really get motivated to react with anything unless you give it a push or a nudge, chemically speaking. But I went there and I saw they had like entire groups that were building equipment just to put them on airplanes, ship, helicopters, what have you, to measure these molecules. Now, what are these molecules? So I'll walk you through it. I have no intention that you should be able to read all of this text. This is just to amaze you and daze you. I hope that worked. That there are lots of molecules and you need a variety of techniques. So the standard air pollution monitoring equipment, okay, which is now also available in our country with pollution control boards, and they have a lot of employment opportunity, are ones for ozone, nitrogen oxide, sulfur dioxide, PM2.5, PM10, and carbon monoxide. These are like standard air pollutants for which our country also has standards. Okay, because we know from the decades of research at what concentration exposure it becomes toxic to human health. And the funny thing is that these are the outcome of years and years of R&D by analytical chemists in the 70s and 80s and even today. And each uses a very different spectroscopic technique. Just for the students, I'd like to briefly mention that. Ozone is measured using UV absorption photometry, primarily the 253 nanometer line. NOx is measured using chemiluminescence reaction. And sulfur dioxide is measured using pulsed UV fluorescence. Carbon monoxide is measured using filter correlation IR spectroscopy. PM 2.5 and PM 10 are measured. It's actually a very accurate way to measure the mass. So there's a filter tape that keeps going, like your old tape recorders, and you have a cyclone that cuts off the relevant, through aerodynamics, the relevant size fraction of the aerosol floating in the air, and then you measure that you beta attenuation. It's called the BAM technique. So this is standard fare, okay? But the problem is when you want to regulate or control these, you are very, very disadvantaged by the fact that they all come from multiple sources. First of all, this ozone is not emitted directly at all at the surface in any appreciable measure. Okay? It's only the child of chemistry. What chemistry? Very non-linear chemistry. You may have studied that VOCs and NOx make it. And the others come from a multitude of sources. So the first thing we had to do was, okay, of course, measure these, but along with these, let's measure the molecules that are going to help us do some detective science here. Like forensic science, like each of these molecules has information in them about certain process, chemically speaking, or certain emission sources. And let's try and measure as many as we can to get a comprehensive set. So for that, we have to rely on a variety of techniques. So this thermal desorption, gas chromatography, flame ionization detection, GC has been around for quite a long time, but to measure in the air at PPT detection limit, you really need a very good thermal desorption unit. We managed that. But the piece de resistance of this facility was really this proton transfer reaction mass spectrometer, which was the first to be deployed and bought by any research group in South Asia. Okay? And this, in 2011, our lab had the good fortune of setting this up, and now we do have a couple of them in the country. And then for greenhouse gases, we measure them using a relatively now well-known technique, but a few years ago, very hot technique, so to say, called cavity ring-down spectroscopy. So what do we do with these ability to measure these molecules? How do we apply it for a concrete societal question? So one of the things is the existing paradigm was that when I was measuring in the Finnish forests or the Amazon rainforests during my PhD, life was so much simpler. Why? Because you are in a very, very well characterized and known atmospheric environment. You're far away from human civilization. Their interest was in pre-industrial chemistry. And so you could just rely on measuring a couple of these molecules. And if you measured a lot of isoprene, you knew you had forest emissions influencing your ambient air quality. If you had a lot of acetonitrile, then you knew that there was wood burning, because this is a product of combustion, biomass combustion in particular. If you were seeing a lot of dimethyl sulfide, these are produced from phytoplankton in the ocean waters. That could be a very good marine tracer. And if you measured all of these sort of other molecules, anthropogenic sources like traffic and solvent, in a remote location like the Amazon or the Finnish forest, these would be adequate to tell you, yes, you have also sampled city air, traffic emissions in particular. But in our great, and not just our, in many developing countries, this is way more complicated. Allow me to explain. If we look at the basic chemistry of the fuel that is burnt, let's take paper, let's take wood, let's take cow dung, right? Most of these biomass have three things that they are made up of: cellulose, hemicellulose, and lignin. And for those of you who are interested in the structure, cellulose is just a polymer of D-glucose. Hemicellulose, you can see, is this type. And lignin has some aromatic moiety, okay, with some substituents. Now, whenever this is burnt inefficiently, and here is the key word, burnt inefficiently. Do you see fires around you in the landfill when the Reddiwala comes to your home, takes the waste, dumps it on some landfill near your city or village, and then time to time it is set on fire? Well, the chemistry that's happening in the flame there is pretty much this, because what happens is these, depending on the stage of the combustion, you can have a variety of reduced carbon compounds that can be formed, and each of these in turn makes up these primarily volatile organic compounds, the ones I spoke to you a lot about just a couple of minutes ago. So basically, this is like an exploded pharmacy. If you go to a medicine shop, you set it on fire, you can imagine what kind of dirty molecules you'll have to see if you had the instrument to measure it. Whenever we light an open fire like this and let the smoke enter into the air, this is actually what we're doing to the air. We're polluting it, not just with the regular pollutants which we can measure and which are monitored, but with a whole lot of other toxic stuff, the effects of which we see on our health. So now coming back to the scientific problem. So we know that this is the complexity now that we have to deal with in this type of smoke. So the first thing our group did over a large, several decades, well, not several decades, but last 10 years, I'd say, is we went around, we devised a method by which we could collect the smoke from each of these different types of sources, which, by the way, if you take a developed country, are extremely well regulated. Their energy use portfolio, in the 50s, 60s, London and Los Angeles sometimes had even more pollution than what Delhi has today. But they managed to clean up their stuff. Why? By a smart switch to cleaner energy portfolio and cleaner technologies. Even their cars have now the right catalysts. Some of you were showing, the experts were showing about how nitrogen, the high temperature combustion in vehicles, that produces a lot of nitrogen oxides. Some of you showed the reduction of nitrogen oxides to ammonia. And actually, many cities now in London, they have an ammonia problem also from the traffic, which wasn't there earlier because the catalysts are so good in the vehicles. But anyway, in our case, these are kind of the sources that are fugitive. If you ask the government about this, because I work with them, thanks to their efforts, they do try to clamp on it. But this is so episodic and opportunistic. Honestly, nobody can actually control it. How do you control a bonfire, right? It's very, very difficult, but this is the reality. So we collected samples of all of these different types, and this is just to show you a picture of how even very similar types of sources. So now let's talk general classification. Fossil fuel and biomass burning, right? Fossil fuel is generally well regulated. We use it in our industries and in our vehicles. So here you can see LPG headspace vapors, you can see petrol headspace vapors. And the only thing I want to, I don't think you can read these molecules. These are just individual compounds, alkanes or alkenes or aromatic compounds. But you can see that the profile looks different, right? If this is what we call a normalized source ratio. So you take the compound that is present in the highest amount and you divide all the others by that. And so you get a ratio from 0 to 1. And this is like your DNA fingerprint. Just like in a crime scene, by looking at the fingerprints that are there, you can trace it to individuals who were there on the crime scene. This is actually a way to build a database for very similar kind of biomass or fossil fuel sources that can be distinguished from each other. So this work has been published in this journal. And you can see even the same source, like paddy stubble, which is very much in the news always at this time of the year in Delhi NCR, that smoldering and flaming stage also has some differences. So the key here is really to have the chemical firepower to be able to measure these. So now we thought, okay, now we have a very good idea of what it looks at the source. Let's see if we can take ambient plumes. So what do I mean by that? Here, we don't know, we just see some, we just measure at a receptor site, like somewhere like here on, let's say, Sri Sathya Sai Institute of IM Learning campus. We measure the air. And you will see that sometimes the values are high of some pollutants, sometimes it's low. And you see different types of plumes. So now if you could use the information we had about which molecules are intrinsic to particular sources, and you do clever analysis, you can see it's possible to even distinguish paddy residue burning from wheat residue burning, both of which are biomass, right? But paddy is burned under very different conditions with a slightly different elemental composition compared to the wheat, which is burnt in summer. And garbage, leaf litter burning, fossil fuel burning, okay? So this is something that gives a lot of hope, and it was published in the Environmental Science and Technology. And this basically completes the part about where I've kind of given you a flavor, not the details, of how the molecular fingerprinting workflow looks like. Now let's look at the real world problems that you may have heard about in the news. So the first thing is Punjab. Here, this is a map of the European Space Agency. The light blue color shows you the irrigated cropland. 15 minutes left. Okay, yeah. And the irrigated, so Punjab is one of these regions of the country which has really done a great favor to the rest of the country. I'll explain how. And I just wanted to mention that we are at a very strategic location, ISER Mohali, where we are able to just sit in one place, and depending on the time of the year, we actually get air mass from upwind in the farmlands, which is the main wind flow direction in all seasons. But also during the monsoon season, we get air from the entire Indo-Gangetic plain, you know, the more densely populated in Uttar Pradesh and so on. And we are just 300 kilometers north of Delhi. Okay, so if you look at this, what has happened to this region over the last 60 years? Let's look at it from a comprehensive point of view. First, of course, the clue for us was when we look at, this is what we call a calendar plot, right? Just like we make our dates for anniversaries, birthdays, etc. This is, sorry, a pollution calendar plot where, thanks to the fact that our facility measures 24/7 the ambient air, so we have very high temporal resolution data, we can say, okay, which days of the year exceeded the national ambient air quality standard. If it's a red color, it exceeded it. If it's green, then it complied with it, right? And for two basic criteria air pollutants, ozone and PM 2.5, right, which is required to be regulated and controlled in our country. And you can see that barring the monsoon season, the rest of the year looks pretty bleak. And for PM 2.5, in fact, there are levels that go up to 300, 400 microgram per meter cube. You frequently see this kind of news that Delhi is the worst polluted city in the world, and so on and so forth. Well, that is primarily based on the measurement of just this one air pollutant, PM 2.5. Okay, and so we saw this, and then we said, like, I'm not from a farming background, so to say. Okay, so I was like very curious, what exactly happens, especially at this time of the day? And this was, I'm talking about this when the awareness about stubble burning was very low. This is about 2013. It was there, but not as much awareness as exists now. I hope in part because of the work that Swami got us to do. So if we look at why the stubble is burned, okay? So this is how it looks like, a burnt field. The problem, why does it occur? For those of you who are like me, perhaps, not from a farming background, when the paddy is sown, it's generally in the monsoon season, and then depending on the rice variety, they become ready for harvest in October or November, sometimes also in December. And now, what happens is that in the 1980s, this particular region, the technology to do the post-harvest operations, which means you remove the rice grain from the paddy stalk. This got taken over by this machine called the combine harvester. And what this does is it removes the grain, no doubt, very efficiently, but it leaves about 1 to 2 meters of the stalk remaining in the field. And in the olden days, when the scale was not so high, people would actually use that as mulch, as fertilizer, as fodder for their cattle. But with the increased scale of all of this, and the narrowing, climate change has also narrowed the window in which this post-harvest operations can take place, and the costs of all of that, doing it manually. Because of that, farmers just set fire to it. Okay? I just wanted to mention, it's not like government hasn't been doing anything. Punjab Agricultural University came up with a different machine called the Happy Seeder. So after So this is a rice wheat growing season. So rice is grown in the summer, and then winter is when wheat is grown. Okay, and so for sowing the wheat, they actually sow it through the mulch that is possible with this machine, but it didn't really take off as it should. Now let's come back to the chemistry part. When the smoke is vented into the air, then this is this cocktail of different molecules. They undergo oxidation, I've told you, they form secondary inorganic aerosol, secondary organic aerosol, ozone, and then the same air which has been polluted by the agricultural burning now turns out to be very bad for the wheat cultivation. So this you see is a cultivar. The only difference between these three is the first one has been grown in clean air, the second one has been grown in air that has only been scrubbed of ozone, but the other pollutants are still there, and the third one has been grown with ambient ozone. So you see the decrease in crop yield, right? Okay, now let's go back to what other discoveries we found. So of course, red here refers to periods affected by the paddy residue fires. That's what the molecule concentration in the air. This is acetonitrile, a very good tracer for biomass burning. You see benzene, which is a human carcinogen. This is one of the few VOCs for which we have a national ambient air quality standard, which is 5 microgram per meter cube annually, which translates to about 1.6 ppb, right? And what we saw here is, in addition to the usual suspects, we actually discovered a new molecule also being present in this, which had a very interesting profile. If you see, this is the middle of the day, right? A peak and an evening peak here. And we saw this more pronounced in the post-harvest period, which is affected by the paddy residue. The meteorological conditions between both of these, when we take the blue and this, the control period, are very similar. There's hardly any difference. And if you look at this molecule, what is it? In addition to carbon monoxide, which was mentioned, right? We see some of the highest levels of carbon monoxide in the world for polluted regions here. Just to give you an example, in Europe, most cities would have less than 100 ppb of carbon monoxide. And here you see in this peak period, it going up to about 1500 ppb. So we found that there's this molecule called isocyanic acid, which is the simplest molecule you can make with 1 nitrogen, 1 carbon, 1 oxygen, and 1 hydrogen. And it's a very close chemical relative of methyl isocyanate, which I am sure you may be aware was the gas that also leaked out during the Bhopal gas tragedy. And so this one, it's formed, this is the chemistry, bonds break, and it reaches out. But essentially, this causes symptoms, not cancer. It causes it denatures the protein involved in eye vision, and also causes arthritis. So there is no surprise that during this period of burning in the village dispensaries in Punjab and wherever this occurs, there is a very high hospitalization, complaint specifically for these two types of problems. So people knew about that happening. They attributed it to the smoke, and we think at least this is one of the contributors that is doing this. So this is just to tell you about that. Okay. So now, this is the workflow. This is actually Prafulla, who's actually a faculty here. Okay, another very nice thing that you can do with this is not just measure individual molecules, but you can basically, by sampling the smoke and applying what is called the carbon mass balance method, because most of the carbon in almost all the carbon in the fuel when you burn it has to end up in the form of a carbon containing molecule. Either it's a volatile organic compound, or it's carbon monoxide, or it's carbon dioxide. So if you do that mass balance with some knowledge of the elemental composition of the primary biofuel, then you can actually calculate emission factors. And this is very useful, because the emission factor is basically a number that tells you how many gram of a specific compound has been emitted per kilogram of that fuel burnt. Okay? So now when you combine this, so this is just a comparison of the different emission factors, what had been published. So some work had been done in the literature earlier, but none from India, within India. People used to take, there's a fire laboratory in Montana, where they take samples from all over the world and they burn them in their chamber. Now you can appreciate that burning it in the real world in Punjab or Haryana or wherever else, or in South India is going to be quite different. There'll be deviations from that in terms of how much you can do in a controlled environment. But for the flaming stage, the emission factors compared well with them. They just couldn't capture most of the smoldering stage. So we published this. And now if you have the information of how much of the stubble is burned. So for this, we use two-pronged approach. We use satellite data to look at the fire activity. That gave us a top-down constraint. But we also took the district-wise crop yield data and surveys in the villages of what fraction of the stubble do they actually end up burning, which is difficult to get, but we got it. And if you do that, then you can come up with maps of each district-wise point 1 kilometer by 1 kilometer spatial resolution, how much of a particular pollutant, this is benzene, this is isocyanic acid, is emitted at that level. And why is this useful? Because weather model, air quality model, any of this, atmospheric chemistry, process-based models, all of them need to get the emissions right in order to have the right output for the right reasons. The basics have to be proper. Okay, the other thing that we were able to help, and this we are very, very gratified by, is that you may have recollected the odd-even rule was implemented in 2016, 2017 for the first time. It so happened that my the research group was in Indira Gandhi International Airport trying to do measurements on fog chemistry at the invitation of Indian Institute of Tropical Meteorology, Pune. But that year, in December, there was hardly any fog. But odd even got announced, and I told the students, look, the action is somewhere else now. So why don't you take one of these busy road intersections where the vehicles don't normally stop? It's like a wind tunnel, and measure the VOC traces for traffic emissions versus biomass burning. Maybe it will be helpful for us to give insights, evidence-based insights on what actually happened when odd-even rule was implemented. And this got a lot of media traction and useful news. In fact, it was even used, I am told, by the Secretary of the Ministry of Earth Sciences, the National Green Tribunal, when the next year the relevant government, state government wanted to again implement this. They said, we are not going to let you do it because this study, we were told to publish it in Current Science, which is well read in the Indian community, shows that if you implement odd even with exemptions, like you are letting the petrol two-wheeler, the other part of the fleet, ply on the road, but only curtailing the petrol four-wheelers, which are owned by private owners, is not going to yield results. So what did we actually find? Two things. We found that, first of all, people, because the public transport infrastructure is not good enough to actually allow people to take an alternative. So if I have to go to my office, I simply, the rule was you don't go between 8 a.m. and 8 p.m. So I simply leave for the office before 8 a.m. or and then come back after 8 p.m. Number one. So we actually saw the emission peak of, you remember these VOC traces, benzene and toluene. There is a shift between the pre-odd even implementation period in the same season to during when it was implemented. It actually shifts. And that is very worrisome. You know why? Because at that time of the day, the mixing layer height, this is a meteorological concept, it's basically the volume into which the surface emissions accumulate. Now your concentration is a function of emissions and volume. So if your volume reduces, then for the same emissions, you'll get a higher concentration. So we saw that there was this spike in the early morning. The other thing was that the most polluting part of the fleet were not even targeted. And what was the proof of that? Recollect the emission factor measurement. Now see how this can be used to inform policy. Here you see the emission factor here in terms of gram per liter of fuel burned. So if it's an LPG fuel three-wheeler, a three-wheeler fueled by LPG fuel, then it has 60 gram per liter of all total NMVOCs emitted. We also did it for CO2 and other compounds. Petrol two-wheeler is here. Look at where the petrol four-wheeler is. So it's like in this classroom, if I hear a lot of noise from outside, and I come and I handpick the people who are the most silent, who have contributed least to the noise, and say, please leave the room. I want a quiet classroom. It's not going to solve the problem. I left the troublemakers or the more contributing people, individuals still inside the room. So these were not at all covered by the odd even. Okay, so this is why evidence-based policy is very important, and we are happy that this actually ended up implementing, and even till date, it has not been allowed with these with the old sort of formulation, right? The other thing you can do is in the fog season, what we found is that when the temperature dips, actually people, in order to keep themselves warm, they burn whatever they can get access to. If they don't have a room heater, they're not rich like us, they can't afford that, then they actually burn that, and those extra emissions end up prolonging the fog cycle. So that we published in this paper. So this is another example of how molecules can help track a process that may have been missed by, and is indeed missed by, the air quality forecasting system. So after we found that feedback, we were able to put a chemical tracer-based method, which Indian Institute of Tropical Meteorology, that does the air quality forecast for Delhi NCR, put in, and they are able to get better forecasts, because earlier the nighttime air quality was completely off. Okay, now finally, this is almost the last slide. We, as an outcome of that odd-even rule work, the Ministry of Earth Sciences, Delhi, the central government, they invited our group, along with Indian Institute of Tropical Meteorology and Indian Meteorological Department, to do a one-year-long study in Delhi with all of our, chemical firepower. So we basically set up a super site there. And two of the students, I should mention, Arpit and Sachin, who did their MSc here, they were also part of the team as project students. What did we find? I don't have time to explain the details of how we do that, but basically we take the ambient real-time data, and then we use a mathematical model. Mathematical models can give you any output you want. So to get it to be meaningful, we take the statistical output of the PMF and then match it with our source finger profiles, which no other group in the world has. And that then drives the mathematical output to a real-world source. What we found in terms of PM2.5, this is gas phase pollution. Just think of it that way, the total VOC, and this is aerosol pollution, right? PM2.5. In fact, the main culprit for the bad air quality and the hospitalizations. If you look at the sources, this is the first study that has been able to resolve very similar type of sources. Always the problem used to be, okay, even if it's biomass burning or fossil fuel burning, biomass burning can be residential biofuel, like when people burn cow dung, when there are tandoors outside, when there's waste burning. How do you distinguish it from paddy burning? So in this, thanks to our chemical profiles and this mathematical model, and the work actually done by Arpit Avasthi and Dr. Babel Sinha, we could actually distinguish and give the contributions of each. And so it turns out for PM2.5, if you want to control this, the most effective is to go after these top sources. I always like to say why evidence-based policy is so important is because otherwise the situation can appear so gloomy and hopeless. If you know that, okay, this can also cause pollution, this can also cause pollution, this can also cause pollution, that is not meaningful for a policymaker. If you say, sir, with this one source or just these two sources, you can bring down 50% of your air pollution, then you have their ear. So this is this. But when you talk about the gas phase pollution, then that's mainly coming from the fossil fuel sources like the vehicular exhaust. So choose your poison according to which kind of sources you would like to remain. And this also calls for the need for a multi-sectoral approach. Often people like to reduce this to saying, I'll wind up now, to saying that, 40% of the air pollution is this or 60% is this. The reality is actually the details are important, and the devil is in the details. Now, one final thing, cow dung is something that our country has done a great job in reducing the number of households that are dependent on this type of fuel compared to the 1980s, thanks to the Ujjwala scheme and other stuff. But even today, though only 9% of households use cow dung in our country, more than 50% of the direct PM2.5 emissions from this sector are just due to these 9% households. So see, this is such a low-lying fruit that if you go after it in a targeted manner, which the government has tried in the past, it can really help. Okay, so I am done with my talk. And this, I think, was already covered. People can read this report in terms of transdisciplinary. I'll just end with this last part here. You know, Thomas Midgley. How many of you have heard of Thomas Midgley? Can you just raise your hands? He was one of the greatest chemists, industrial chemists ever. He single-handedly, unintentionally, he meant well, okay, brought the world to two environmental disasters. First, in the 1940s, the fridge industry was using ammonia as a refrigerant gas. So he was working with DuPont in Denver, and he came up with the CFCs as a substitute. And CFCs were great. He sold it as his, and at that time, that was the current understanding. People had not realized about the ozone hole being there due to CFCs. He said this is completely benign, nothing happens to it in the troposphere, and it doesn't, I can inhale it. He even did some demos like that. And then later, of course, we know what happened with that. And then in the 1970s, 60s, 70s, tetraethyl lead was used as an anti-knock agent in petrol. And lead has since been banned because we know its harmful effect. But he was again the person who did it. It helped improve the efficiency of the fuels. And this is just to mention that at the when now with all this past history of environmental research, we should learn and not repeat the mistake. We should have a proper environmental impact assessment before we introduce new chemicals. Thank you so much for your patience, and sorry for exceeding the time. Yeah. Okay. Saira.
The floor is open for questions. We'll take 2 questions.
Question here.
Saram sir, thank you for a wonderful presentation, sir. So my doubt is regarding what is the role of airplanes and other military air services in air pollution? Since airplanes and everything work on combustion of fuel, what is the significant role in air pollution since they are in direct contact with atmosphere?
Yeah, this is a very good question. Actually, the airline industry is a contributor, but mainly to nitrogen oxides due to high temperature combustion in the upper atmosphere. Okay, the ground level contribution is due to fugitive evaporative emissions near the airport, so to say. But those are, with modern technology, fairly well controlled. See, one of the things is that in our perception, when we look at a power plant, when we look at a smog tower, when we look at an airplane, these are all large objects, right? So they give us the impression that perhaps they are doing much more damage than, let's say, a small fire. But how would you react if I told you that a 10-year-old motorcycle, if you measure the exhaust of that and compare it with a CNG bus, the CNG bus, which is bigger, is actually much better. So what I mean to say here is that the industrial technology is still better regulated than your open burning of whatever, waste, residential biofuel, stubble, agricultural waste. So if we can tackle that part, which the developed countries have already done, then at least we'll come to a level where we have to deal only with the industrial pollution sources, which are much more easily to regulate at the point source. I hope that answers your question. And just one last trivia, you may want to search that. In fact, Concorde aircraft were thought to be very, very bad for the atmosphere because they would be flying in the stratosphere. You know, they have to meet the speed of sound, go faster than that, supersonic aircraft. And they banned it because it was economically unviable for them from Paris to New York. Thank God for that. Because if they had not done that, then we would have a greater damage to the ozone ozone layer in the stratosphere, even in the northern latitudes.
Sairam, very exciting talk, and what I would like to call as pragmatic science, because this is something which is directly influencing our lives and society. Sairam, one question I had is while you are concentrating on the burning aspect of say paddy and agricultural produce, there is also a lot of kind of waste that we are generating which goes into landfills, and that is even without burning. There is landfill that if you go into those places you get that obnoxious smell, which is I'm sure has lot many carcinogenics in that. So is there any attempt to look at that direction?
Yeah, Sairam, thank you, sir. Very nice question, because it allows me to put another point that I couldn't cover in the talk, which is that, again, when we talk about agricultural burning, stubble burning, Diwali, yes, these are bad because they occur in a very, narrow time interval, but they are episodic. They don't happen throughout the year. Sir, the source that you just now mentioned is something that happens all throughout the year. And if you enter Delhi, Delhi has 3 nice mountains. These are not geological formation mountains. Anyone who has done the trip to Delhi would see that. You're greeted by that. And yes, in terms of greenhouse gas emissions, some of studies have actually looked at how much waste fills generate methane in terms of the anaerobic. During our Delhi project, we didn't just sit and measure at one place. We also collected, so what we did was like this, detective science. So you can do what is called a windrose pollution plot. So essentially, you are measuring a molecule, right? And then you see what are the high concentrations of the molecule in terms of the directional dependence and the wind speed. So that kind of tells you, okay, if the high values are always seen for benzene, let's say, from the northwest sector at low wind speed, then I can actually, with the other knowledge, constrain, look at Google, use Google Earth, look at what kind of industries are there. And then what we did was we relied on our actual measured real-time data with the mass spec and the GC and went to those sources and collected the source samples there. So to answer your question, in fact, in one of the reports that the government asked, I mean, they always ask for this kind of inputs, we mentioned the same thing, that if you want to solve India's, or for that matter, the developing world's air pollution problem, it's really down to one line. It's a waste management problem. The problem is, in our part, the awareness to segregate the waste at source. And then we even sort of, to provoke people, did a study where we said, okay, somebody mentioned about upscaling plastic, which was, I thought, a very nice thing. We said, if you burn plastic, suppose you just don't have the LPG cylinder, but suppose in your own stove, we tested different types of stove, you replace the cow dung with plastic, does that give better, less toxicity and better? And the answer is yes. So we call that paper Replacing the Greater Evil. But I would say that these are all short-term interim goals. You know, in one go, if we say we want to decarbonize, that's not going to happen. We want to leapfrog. So we should have a smart selection of medium to low hanging fruit, evidence-based, which we can go after in this. But yes, waste burning is indeed the air pollution problem of the country. Okay. Okay, thank you. Sairam, and again, apologies for the extra time.
Sairam. We thank Professor Vinayak Sinha for highlighting the importance of greenhouse gases in maintaining temperature of atmosphere, effect of anthropogenic gases like volatile organic compounds, VOCs, which later convert to carbon dioxide, ozone, aerosol particles like PM 2.5, secondary organic aerosol in raising global temperature, significance of wet belt temperature, analytical tools used to measure carbon dioxide, carbon monoxide, PM 2.5, ozone, etc., to understand the reaction pathways, VOCs as chemical tracers of sources, side effects of inefficient biomass combustion, chemical fingerprinting of emission sources to identify the source, agricultural practices which has affected air quality, effect of isocyanic acid to the human health, outcome of the 50-50 rule in Delhi, Whitefield, and why evidence-based monitoring is important for targeted intervention. We'll now request our senior faculty, Professor G. Nageshwar Rao, to offer our token of love, Professor Vinayak Sinha. Sai Ram. The second speaker for this afternoon session is Dr. B. Venkata Sharada, Scientist F, Center for Nanomaterials, International Advanced Research Center for Powder Metallurgy and New Materials, Hyderabad, Telangana. Dr. Sharada will be addressing us on the topic Materials and Processes for Energy Storage Applications. We request our student Amaya to introduce and invite Dr. Venkat Sharada. Sai Ram.
Sai Ram. It is an absolute privilege and honor for me to introduce a truly distinguished scientist, an inspiring mentor, and an exceptional leader, Dr. B.V. Sharada. Dr. B.V. Sharada is a senior scientist at International Advanced Research Center for Powder Metallurgy and New Materials, Hyderabad, an autonomous research institute under Department of Science and Technology. Her journey in science is nothing short of inspiring, an extraordinary blend of academic brilliance. Dr. Sharada's academic journey began with her intermediate from Board of Intermediate Education at Sri Sathya Sai Women's College and BSc from Sri Sathya Sai Institute of Higher Learning, followed by her MSc from Sri Venkateshwara University. She then pursued her MPhil from the Central University of Hyderabad before earning her PhD from the University of Tokyo. It was at this prestigious institution that she worked on highly conducting diamond-thin films and microelectrodes with a specific focus on their application in biosensor and water treatment. Her excellence in research has not gone unnoticed. Dr. Sharada was awarded JSPS Fellowship both during her PhD and postdoctoral work. She also worked as a JST Fellow under a pre-venture project for a technology-oriented program. Upon her return to India, she joined ARCI as a DST woman scientist at Hyderabad and is now working as a senior scientist at scientist level F. Her leadership at ARCI is exceptional, particularly as a coordinator of the Biomedical Materials Research Group, where she leads research focused on material for biomedical implants, energy storage, and conversion. Her innovative work spans a broad range of materials from nanostructured composites for energy application to advanced titanium-based materials for both photovoltaic and biomedical use. Her contributions to science are extensive and impactful. She has authored over 75 research publications, contributed to 7 book chapters, holds 15 patents, and has been involved in the transfer of 3 technologies to industry. Beyond her scientific achievement, she has a deep commitment to the scientific community. She is a member of several prestigious organizations, including the Electrochemical Society of India, the Material Research Society of India, and the ASM Hyderabad chapter. In recognition of her outstanding contributions to science, she was elected as a Fellow of the Telangana Academy of Science in 2020. It was an incredible privilege for us to have Dr. B.V. Sharada here with us today. Please join me in welcoming Dr. B.V. Sharada.
Shri Sai Ram. Fine. No? So my humble pranams at the lotus feet of Bhagwan. And I first of all thank organizers, including Professor Bandari, for calling me back to my home. And thanks to Ms. Amaya for her kind introduction about me. I have studied here for 5 years, and after coming back to India, I have made several visits to our institute, and most of our students from here have also worked with me at ARCA, obtained their PhDs, and are at good positions now all over the world. So the topic of my presentation today is materials and processes for energy storage applications. It goes very close to the topic of our workshop today, chemistry for sustainable future. So all my previous speakers have mentioned about what is sustainable future. So this is also a part in putting efforts for the sustainable future, and energy storage applications are for both stationary storage and electric vehicle applications. Till now, most of the vehicles have been on gasoline, which is causing, my previous speaker has already mentioned, it is causing pollution, although not as much as the stubble burning, but including villages and most of the cities, it is the major cause of concern, causing pollution within the city, causing several health effects also. Now, bringing electric vehicles onto the roads will solve most of the problems, and India has mainly three-wheelers and two-wheelers. So how we are trying to solve the problem for these two-wheelers and three-wheelers, I will show. So I am from ARCA, as already mentioned previously. This is an autonomous research and development institute under Department of Science and Technology, with a special mandate of translating research into technology and transfer to Indian industry. Yeah. So our research institute has worked under several centers of excellence, 9 of which are at Hyderabad and 2 of them are at IIT Madras campus. Yeah. So I personally work at the Center for Nanomaterials, concentrating on both energy storage, energy conversion materials, as well as the biomedical materials. So I'm basically from physics background, but then turned into a material scientist, now working more with the chemistry. So I think the scientists are always like that. Most of you must be having that experience that you merge with the other scientists and start working on the latest issues. Yeah. So the second line of it, bridging science and society. So science and society are always bridged. You can see over here this triangle. The scientists invent using science, and then what bridges the society and science is the technology. So once we invent something, patent it, publish, and leave it over there, it really doesn't come into society. It is not very useful for the society. So we always have to think of how to innovate and bring it into technology. So the technology helps in bringing the science to society, but society always has more and more needs. So the scientist's job is to work to address all these needs of the society. So as one of the, so for energy storage, of course, for the electric vehicles. Second is the stationary storage applications you can see over here. So this is from the wind energy and that is from the solar energy. These are the energy sources where you can see every day there is a pattern change because of the wind patterns. And also in converting solar energy, you can see on a cloudy day, there is a lot of disturbance, and even on a sunny day, you can see from 11 to 3, I think it is maximum power coming from the sun, and that has to be converted into electricity, and you need proper energy storage devices before it goes to grid also, so that the whole system functions properly. So, okay, I'll skip this because it's almost the, so these are all the different energy storage devices that are used when the energy is converted from renewable sources and they store it. We mainly are working at ARCI on hydrogen storage, fuel cells, electrolyzers, batteries, and supercapacitors. I personally work on batteries and supercapacitors, so I'll be mentioning only these two in today's presentation. Yeah. So what is the difference between a battery and a supercapacitor? You can see over here, battery has high energy density, whereas supercapacitor has a high power density. So it charges in minutes and also discharges in minutes, whereas battery charges in hours and also discharges in hours. So if you can have a combination of supercapacitor and battery, you can have a very good system. I'll tell you in my next few slides how it works. Yeah, so it's to be understanding it better, you can see. Supercapacitor works like just throwing a cup of water, whereas a battery works like this. Slowly it comes out, and even the filling is very slow. So now nano has been the buzzword in the last decade, but now people have forgotten nano. Now they have been saying energy storage, energy conversion, but in all these applications, nano is there. Unless you have these nanomaterials, you are not able to increase the efficiency of the materials. So we have been using all the the materials in the nano form only for all these batteries. So we work on sodium-ion batteries, lithium-ion batteries, lithium-sulfur batteries, supercapacitors, and all these forms of nanostructures are used for making these electrode materials. Yeah. So why I am showing this? All of you must be knowing. About 2 to 3 years ago, we had a lot of fire accidents with the two-wheelers. Why this has happened, any of you know, the students? There are two reasons for this to happen. One is using a material which is not tropical friendly. Second is depending mainly on the materials which are imported. These are the two reasons why these things happen. The first is a material called lithium NMC, lithium nickel manganese cobalt oxide, is used in most of the four-wheelers all over the world. And India also started using both for two-wheelers and four-wheelers the lithium NMC material. So, but NMC has a problem when the temperature increases above 50. It immediately catches fire. The four-wheelers do not face much of a problem because it has a very good thermal management system. So because of this thermal and in four-wheelers you have place even for keeping the thermal management system, whereas in two-wheelers, two things again. One, it should be cost effective. Second, the place is too small to have this thermal management system. So when you use lithium NMC, without thermal management system, if you keep the scooter under the sun, even without running it, it catches fire with the Indian summer temperatures. So this is what has happened, and many of the scooters caught fire. And second is using unwanted charging systems. People even took them home and charged the batteries. Because of that also these fire accidents happened. It should not happen, but why it happened is using the compromised material which is coming from our neighboring countries. So that means that we have to make our own materials. So ARCI is working towards that. Yeah. So what I was just mentioning is over here in this graph, you can see the materials which are in the red, and both at the top and the bottom. This is for the anode materials of lithium ion batteries, and the top are all cathode materials. So the materials which you can see in the red part catch fire very easily when the temperature increases and when there is no thermal management. And also at the bottom, the graphite and germanium, lithium or lithium alloys, all these catch fire very quickly. But what is most commonly used is lithium iron phosphate. Can you see? The lithium iron phosphate is a tropical battery material. And when ARCI started working on it 10 years ago, people have said whole world is using NMC. Why are you going into LFP? This is one material which no one takes from you. But we had a lot of brainstorming sessions, and that time our director said, no, this will be a material for India. So we started 10 years ago, and it took 10 years for us to come from the invention stage to technology. So bringing one invention to a technology is not that easy, because what we do first in the lab is making in few grams or milligrams. And then we get very good results, we publish, we patent first. So one more thing to all the students is, when you have a very good result which is very novel, first patent it. Many people lose it over there. They cannot bring the technology because it is published. Out of our eagerness to get more publications, we publish first, then we lose the technology because it's already out and nobody takes the technology. So first patent, then publish. But when you patent, you don't leave it over there. You try to upscale from few milligrams to few grams, and few grams to 1 kilogram or 500 grams. And my personal experience, I'm telling, it takes years for that also. Because when you make in a small, morning someone was speaking about ball milling. Actually, we have used only ball milling process. It's a solid state extraction process, which was very easy for few grams. But then when we went to kilogram level, the uniformity was a problem, composition was a problem. Everywhere the innovation is required, and you require a group of physicists, chemists, mechanical engineers, electrical engineers. Everyone is required for bringing science into technology. So here you can see, as I said, the nano size is very useful because its diffusion length is lower compared to a micron-sized particle, and that helps. You can see over here, a micron-sized lithium iron phosphate. These are called charge-discharge curves, those who do not know, for a battery. And when you use a nano-sized lithium iron phosphate, you can see very good charge-discharge curve, and you can see 150 milliamp hour per kilogram. Whereas here with micron-sized particle, 50 milliamp hour per gram. So you can see a 3 times difference in the performance of the battery when you use nano-sized particles. And now, as I mentioned, when we make from grams to kilograms, you can see, I will show in the next one. So you can see over here, we made first in few grams, then we used a flame spray pyrolysis process. This is one more point we should remember. From when you are making small quantities, you can use expensive process and expensive equipment, expensive chemicals. There is no problem. But when you want to upscale it, we have a very big pilot plant facility of flame spray pyrolysis. It made very good nano-sized lithium iron phosphate particles, and we made devices, and we have seen that it is also performing well. So we wanted to give this technology to an industry. So 2 or 3 industries have come. What happened is they asked for cost. Per kg, how much is it? Okay, so we calculated, and when we have shown, it shows that it is expensive compared to what they are importing from abroad. So then we had to close this process, look for another process which is cheaper. Then we went for this ball milling process. You can see over here. Again, in the same high energy ball milling, this is an equipment that we have imported for 1 crore from abroad, and we have used this. Again, it gave very good properties. When we do the costing for this, again, because of the 1 crore of the equipment, the total material cost has gone up. So again, the same problem. So now we have collaborated with, there is something called GOCO model. I don't know how many of you know. That is, government and company collaborate together even before the IP comes and see how things can work out. So we collaborated with an industry and we brought this milling unit. This is called attrition milling unit, which is giving the same performance as the high energy ball milling. And with this, we got almost the same performance. You can see over here with the Zos milling and the attritor 140 and 138. So each step has taken about 6 months to 1 year, but then we have reached the technology stage. And then the next problem is how to validate these materials. If I say my material is very good, no industry takes it. I have to validate at another unit which says that my material is good. Then we have taken help of IIT Bombay, Professor Sagar Mitra's lab, and we have made with our material the cells, 18650 cells, and this is sent abroad to validate them and show that they are on par with the commercially existing ones. And now, after this whole exercise, this industry has come forward to take this technology, and this technology is the first in India for the materials. Why I'm saying is, all the EVs, the modules are made in India, but the devices, that is cells and the materials, are imported from abroad. Even the cells are imported from abroad because there is no material made in India. So this is the first material that is completely Indian, and this startup has taken our technology even to make in India and also abroad, so that we also get the export experience. And we are also helping them by incubating into our campus. Why I am telling to all the students is, now you are researching, okay, you are publishing, but think of even a startup for our own country. Think of indigenization of materials, devices, and also equipment. So for all these things, you should be inspired to see seeing these such type of technologies, so that we get our own materials in India and need not depend. Suppose there is a war somewhere, it should not happen, then we don't get the materials. So we can have the technologies to make in our own country. Nothing like this. So this is incubated, and now they are making 10 kilograms per day, and they are setting up a big plant next to Amar Raja batteries, which is making the devices. And by 2026, the materials will be out in the commercial market. And LFP-LTO, which is called a super battery, can be made using these materials. And so now this has solved the problem of tropical batteries. The next is, we need more energy density, because these batteries are a little bigger for most of the vehicles. I want even in two-wheelers. So the next generation battery material is lithium sulfur battery. That is, it has lithium as anode and sulfur as cathode. The advantage of this lithium sulfur battery is that it has 1672 milliamp hour per gram, which is almost theoretical energy density is 5 times higher than that of lithium ion batteries. So it can be used even in aviation. You can see over here, one of the British companies has just demonstrated that it can run several kilometers, 230 miles they have shown by running using the lithium sulfur batteries. But no research is as easy as we speak, isn't it? This has its own problems. So the lithium sulfur battery, although the energy density is very high, and you can see the cost for driving range is very low compared to lithium ion batteries. But however, the problem with the lithium sulfur battery is that it forms polysulfides during the discharge. So sulfur forms Li2S8, Li2S6, Li2S4, Li2S2, Li2S. So all these middle order, higher order and lower order polysulfides, they especially the higher order polysulfide dissolve into the electrolyte, and they reach the anode and they deposit on the anode. Because of this, what happens? The sulfur slowly goes along with the lithium, stays with the anode, and the cycle, the energy, the specific capacity keeps coming down with each cycle. So because of that, what happens? See, you can see over here very clearly. At each potential, you can see S8, which starts from 2.7 at 2.4 or 3, Li2S8 forms, then Li2S4, Li2S2, and Li2S. So now what we need is only Li2S. We don't want all these other polysulfides. So how to make this possible? So we have tried different ways to do that. So this shows how to address all the challenges that, yeah, you can see over here, the porous sulfur host withstands volume change. So we need to have a porous, sulfur is an insulator, isn't it? So this sulfur as it is, if you use, it doesn't work as a cathode. So you need a conducting medium. So we have used highly porous carbon host for sulfur, and this solves the problem to an extent, but not to that much extent. Then how to arrest this shuttle behavior? So you have to keep this sulfur inside the carbon. So what we have done is we have modified or embedded metal nanoparticles onto this carbon. This work as electrocatalysts, and these electrocatalysts see that the shuttle effect is minimized and you can have better cycle life. And the last one is to use directly small chain sulfur molecule. So this also addresses the shuttle effect to an extent, and you can have longer cycle life. And this, of course, like any other research group, we have started with a biomass. We used banana peduncle, that is not the banana stem and all. The banana peduncle is a real waste. So this is brought, my student has brought it from the Sangareddy market. She is a collaborative student between IIT Hyderabad and ARCI. So she bought all the, she just brought, no need to buy this because it's a waste material, from Sangareddy market, and she has made activated carbon from this, and we have seen that this has given a good performance. But then when she is from Kerala, she went to Kerala and brought some more. Okay, then what happened? Can you guess? The behavior is different, because the banana peduncle grown in Telangana and bananas grown in Kerala are entirely different. And the yield is also about 28 to 30%. So again, upscaling becomes a problem, because I cannot give for each state and each country, this is the recipe for your banana peduncle. So for research, biomass was very good, but then for baking it into technology, it was not so useful. Then we patented, but then we could not, see, all patents need not go to the technology level, but this gives an understanding on how to proceed with the research into technology. And then what we have done is, we have, I just mentioned, no, we have used nanoparticles of iron and cobalt into carbon, and we have used a chemical process. Yeah, we have used a chemical process. So here it's all constant. There is no problem. Batch to batch, it was giving perfect performance. And then we have tested the electrochemical. Oh, so this is the TEM image. You can see those metal nanoparticles embedded into carbon. And then the lithium sulfur battery always works when there is 70% sulfur and 30% other conducting material. If the sulfur goes below that, our energy density will be very low. And you can see very good cyclic voltammograms. Of course, this without iron and cobalt, and with iron and cobalt we have tested. And you can see over here, it gives very stable cyclic voltammetry. And this is the charge discharge curve. You can see that it is very good. And one more thing is mass loading, like how much weight do you put of the active material into the cell is also very important. So first, to understand the material, we use lower mass loading. We used only 1.8 milligrams per centimeter square. And then when it has given very good performance, we slowly, you can see over here, this is how much? It's not written here. But anyway, this has given about 1200 milliamp hour per gram specific capacity. And the most important is what I was mentioning here. The cycle stability should be good. So you can see over here at 2, I don't know if you know 2C, 1C and all. So it is how quickly you charge it. So 0.1C, 0.2C, we calculate in those terms. So how quickly you charge it, how slowly you charge it. So at 2C rate, you can see that it is quite stable. Then we have increased even the mass loading. We have taken to 4 milligrams per centimeter square, and even with high mass loading, it has shown very good performance. Now, we patented it, we published, and now we are in the process of upscaling, and the industry is waiting for us to show even at 1 kilogram quantity. Then they said they will be taking it up and working on technology part of it. Then this is also for the lithium sulfur battery, where we have used jute stick. So the jute stick, I will come back again for the solar, when we speak about the supercapacitors. Jute Corporation of India, which is in West Bengal, has written to our director, we have lot of this jute stick waste. So can we do something useful with that? So they have sent us few kilograms of jute stick, and we have converted into activated carbon by, okay, so I'll come back to that. And used it for supercapacitor. As I said, what is a supercapacitor? Which charges very quickly with very high power density and discharges also very quickly. So this is used all over the world, especially in Europe and China, in these city buses or trams. You can see over here, by the time the passengers get in and get out, these bars come up, connect with the electric wires, and then they get charged within a minute. Then it runs for about 5 to 10 kilometers. So this reduces lot of burden on the grid for them. So this kind of, this is a supercapacitor. So this kind of research we have also worked on. Here the advantage is that in case of lithium ion batteries, what is the major disadvantage for us in India with the lithium ion batteries? The lithium source itself is the problem. Of course, recently we have found in Kashmir, Jammu Kashmir, but the problem is we do not have extraction technologies. So we need more metallurgists to do that. But by then we need to also look for alternative materials. So we are also working on sodium ion batteries. Sodium is abundant in India, isn't it? So we can use that, but the energy density of sodium ion battery is still little lesser. We are working on how to increase that. But after the lithium ion battery, supercapacitors for the high power applications, you can see over here, there are 2 types of supercapacitors, which is working completely on EDLC, that is electric double layer capacitors, just like capacitors. And the other one is on redox behavior, that is it oxidizes, you keep a small metal oxide particle along with carbon, and that gives a redox behavior, and you can see that the current density is very high, which results in very high specific capacitance. And one more advantage over the carbon supercapacitors is that it gives, it is useful for even biomedical devices, because it makes use of only aqueous electrolytes, unlike the carbon-based EDLC supercapacitors. So now we also worked on this. Yeah, to make a supercapacitor, this is first carbon-based supercapacitor, and this we have made equal to what is available in the market. Maxwell is the only company that is selling the supercapacitors, and we could show that our supercapacitors, this is ARCI's supercapacitor and this is Maxwell supercapacitor. It is showing exactly for the same size, that is same area of the electrodes, it is showing on par with the commercial supercapacitor. And so this is a project done in collaboration with HPCL. So ARCA does, again, research in 3 types. One is we have our own research, which we do along with our PhD students. We patent, then we go to industry, or industry comes to us to tell any technologies to take over. Then we mention them. The IP completely stays with us. They buy the whole technology. The second is an industry or a PSU comes to us, says that we have this problem. Can you solve it? Then we do along with them, and then the IP is shared by both, and it again becomes a technology. So here HPCL has lot of oil refinery waste that is called pet coke. So this pet coke is a big problem again for all the oil refineries. Again they said, can something be done? So this is again made into activated carbon, and we found that the jute stick, again the yield is only 28%. So with 28% yield, we need lot of efforts to upscale to 10 kilos or 100 kilos. So then we found that this is giving almost 60% yield for the activated carbon, and we further progressed by making the activated carbon material by using the waste material from HPCL, and once it is giving good results, they have sponsored for buying all this pilot level equipment, and we have made this cylindrical cells of supercapacitors and shown that it is working out well. And then what I was mentioning is the aqueous supercapacitors for the biomedical applications. I already mentioned that, see, compared to EDLC supercapacitor, you have much higher current density, and once we have Ki, potassium iodide, as the electrolyte. So the electrode has redox behavior, and if you use an electrolyte with the redox behavior, it gives much bigger current, and so much bigger supercapacitance. So using this, we have got, you can see over here, in aqueous electrolyte, we have got a wider potential window and specific capacitance on par with the non-aqueous supercapacitor. So this we are going to use for the biomedical devices, because this we can use for small supercapacitors. See, there are some applications like EV where you need huge amount of electrode and big supercapacitors or batteries, whereas in biomedical devices you need very small, chip-sized supercapacitors or batteries. So we are working with the aqueous supercapacitors with that, and we have supercapacitor batteries, we need few thousands of stability, whereas supercapacitors, because of the very fast discharge cycles, you have to show at least for 25,000 to 30,000 cycles, and we have shown up to 10,000 cycles. You can see over here that it is doing very well, and now this is also ready for technology transfer. But in case what I have shown previously is one electrode is carbon and one electrode is metal oxide. So there is a lot of difference in the mass balancing and also the capacitance balancing. So if we can have metal oxide on both the sides, it is supposed to be giving much better potential window, and also the capacitance is much higher. So we worked on that also. With the nanostructure, again you can see over here, with the nanostructured materials, we have got very good potential window over here, and also in hundreds of order of specific capacitance, and we made this into a pouch cell. So in batteries, there are 3-4 types now. One is a coin cell, which we do only at laboratory scale. Other is a cylindrical cell, which we are seeing everywhere. The cylindrical cells, which are of several form factors. The other one is a pouch cell. This is a much better form of a battery with better thermal management. You can see over here, this is a small pouch cell, but now recently, I don't know if the chemistry students who visited ARCA have seen that or not. The pouch cell facility for 10 ampere hour system. So now we are making with that, and this is a better form of batteries for thermal management. So even for lithium sulfur batteries, it can work well. And then the final one is circular economy. Someone was mentioning in the morning, the circular economy is also very important, especially for materials like lithium. So we are using our mobile phones. All of us have mobile phones, 1 phone, 2 phones, and everybody changes every 2 years. what is happening to all this lithium? They're all lithium-based batteries, isn't it? So all this lithium cannot be just thrown out. There is no proper system in India still to recycle, although there are many recycling companies. They are importing black mass. It is called black mass. They are importing black mass from abroad and recycling. But we should also have a system to collect all our batteries and do it. And if with mobile phones and laptops, if this is the situation, when the EVs come into, because Indian government has set a target, isn't it? By 2030, what percentage of electric vehicles? 30%, I think. 30% of the vehicles should be electric. So then we'll have lot more wastage of lithium ion batteries. So one way to address this problem is that we have to recycle. So there are different ways of recycling, getting the metals separately, lithium, iron, cobalt, manganese, and nickel. Or just make as an electrode again, okay, by using either electrometallurgy or pyrometallurgy. So what we have tried over here is we have taken the black mass of lithium NMC and we have made an electrode for the supercapacitor, and this has given a very good result, and we have shown this this we are upscaling now as a part of circular economy. Yeah, this is all about batteries. So one more battery that is coming up very quickly now is the sodium ion battery. Why it is not going back? I want to go backward. Go backward. Still. Further. Still. One more. Yeah. So sodium ion battery. So for sodium ion battery, nothing is commercial anywhere in the world. So sodium vanadium phosphate, sodium layered oxides, nickel cobalt layered oxides, they are all the materials under research, but nothing out of them. They are all at pilot level. Industries are testing, electric vehicle companies are testing and all that. Still, it is very, except for 1 or 2 companies in China, nobody is selling these sodium ion batteries. So now it is time for us to work very quickly on sodium ion batteries at least, so that we don't lag behind. And the easiest to start with is carbon, because we have plenty of carbon sources. I'm not speaking about the cathode because sodium vanadium phosphate, again vanadium is required. Sodium nickel cobalt oxide, again nickel and cobalt are required. But the easiest to work is on anode. For lithium ion battery, graphite is used as anode. But for sodium ion battery, it is not graphite. Graphite doesn't work. It is hard carbon. You know the difference between hard carbon and soft carbon, or graphite and hard carbon? You can see over here, this is graphite and this is hard carbon. What is the difference? Graphite is nicely layered. Hexagonal structures in the layered form is graphite. This is mostly used in lithium ion batteries to give very good performance, whereas sodium ion batteries require further different chemical processes that take place. Sodium ion is bigger than lithium ion, isn't it? So it cannot be inserted into this. So the hard carbon is required. Hard carbon is something like with very highly disturbed structure. And one more very recently coming up is soft carbon. So this is graphitic, but it is not completely graphite. It is not completely hard. So it's in between. So these two are the materials that any college can do. So constant, all the chemistry people who are working, I heard some people are working on batteries and supercapacitors. Please work on this, because there is a very high demand for the hard carbon and the soft carbon, because next sodium ion battery is the next generation battery in India and all over the world. So now this is all the story about the batteries at ARCI. As I said, I am also coordinating the biomedical group. There is a huge necessity for the biomedical implants in India. Yeah. I'm sorry, I think I'm moving it very fast. Yeah. So biomedical implants is one more field where we are importing almost every implant from abroad except for stents. So this is one more field we have to work on the different materials, and at ARCA we have all the facilities we have established right from software to 3D printing. We do the metal additive manufacturing for the cobalt chrome alloy or titanium alloy, and we also prepared, you can see these are some of the examples. But however, at ARCA, we don't have the expertise in bio side. We are all material scientists. So we have a sister institute, Sri Chitra Tirunal Institute of Medical Sciences in Kerala. So they do this in situ, in vitro, in vivo testing for us. And some of these materials have come close to animal testing. And this stent, this one with TIN coating is now inserted into a pig at Sri Chitra Tirunal Institute, and since last 2 years, it is performing very well. And I think once it gets a clearance from the ethical committee, it will be commercialized by them. So this is one more field we should also work on for the biomedical implants. And to conclude, this is the formula for us. So we have all our institutes, government institutes or academia working at low TRLs, as I said in the beginning of my lecture, publishing and leaving it over there. And there is industry, that is private sector, which is buying technologies from abroad and making over here. It's just make in India, not really indigenous technology. So we need to bridge a gap between these two. Right from the, we call them in terms of TRLs, technology readiness levels, right from 1 to 9. It should go within India. So I want all the next generation to work towards this. So I just didn't want to speak only on the basic sciences. I wanted to put into all of you how we can go to the technology level. Thank you all.
Sairam, the floor is open for the questions. We'll take 2 questions. One question from the Anantapur campus.
No one has anything to ask?
Anyone from the PSN campus this side? Yes.
Yeah.
Compared to batteries which are made up of upscaling plates or even what do you think about those made out of solid state polymer based batteries?
Yes, this is one topic I did not touch, but the next generation is solid state electrolyte. We are also working, but we didn't go to that level, so I didn't touch upon that topic because I just concentrated on the technologies. But yes, the solid state electrolytes will solve almost all the problems of either batteries or supercapacitors, especially the stability of the devices. But what is the problem with solid electrolyte? Generally, either polymers or ceramics are used as electrolytes. And the problem with these materials is very low ionic conductivity and brittleness. In case of ceramics, in ceramics, people use either oxide-based ceramics or sulfide-based. These two have brittleness. So when you keep between the electrodes, that anode and cathode, they are becoming brittle. So people are trying with polymer oxide composite. Okay, polymer has different set of problems, but you may be seeing in news every day when a company is announcing. Now solid state batteries have already come up and they are ready to be commercialized. But still there are issues they are solving, but probably in 2 or 3 years they will be up. And they are the best batteries with solid electrolyte. Okay? Yeah.
We can take one more question.
Sarah, ma'am.
Yeah.
I have a short question. So, today, if we talk about the market is using more cylindrical cells
Yeah.
through like Tesla, all of this. They use the Panasonic technology,
Yeah.
and yeah, it's done in combination with thermal insulation sheets, and yeah,
Yes.
multiple companies are working on. And you're talking about pouch cells,
Yeah.
like BMW and many others use that. Where do you see the cost benefit? Like, is pouch cell technologies going up in terms
Yes.
of capacity
Yes.
to fulfill that? That's better off, or the other way around?
Yes. Even in cylindrical cells, initially everybody is using this 18650 form factor. But now people are moving slowly towards the 32140, 4060. Now Amar Raja had come last week to us. They said they don't want 18650. They want 34140, 32140 or 4060. So they want better form factors, and compared to cylindrical cells, pouch cells have better thermal management capability. And now China has already come up with blade batteries. I don't know if you have heard of it or not. So you have heard of it. So blade batteries again will be the next generation batteries, but pouch cells are a better choice compared to.
Cost-wise, pouch cells are still not
Yes,
giving the
that
delivery.
is the future. See, cylindrical cells of lithium itself. When did Professor John Goodenough start on lithium ion batteries? Probably 60, 70 years ago. And he won the Nobel Prize when he was 95 years. He started when he was assistant professor. But it came into market. Since last 2 decades, the cylindrical cells are into the market, and so they are doing very good. And that has attracted attention of everyone, and he won the Nobel Prize also.
True.
But now these pouch cells or the blade batteries will be the future. Slowly, but again, we have a pouch cell line, and I know what problems we face. The alignment is the biggest issue. Because cylindrical, you just make a jelly roll and make the cell. Whereas in pouch cell, you need to have perfectly aligned these Z-type layers. That is the biggest challenge. So now what we are doing is we are cutting into that size and then stacking.
So do
But
you
that
do
is-
laser cutting, or do you do mechanical cutting?
We have laser cut. We do the laser cutting. But still, because what we have a semi-automatic machine. So then there will be small issues, no, because budget. Again, government institute, no, so we cannot go for. So, but Goshen in China is making blade batteries already, which is the next generation of pouch cells.
As you know, that electric two-wheelers are coming in the market.
Yes.
Both containing the lithium batteries or lead batteries. Okay.
Yes.
So what's your suggestion to charging the two-wheelers in daytimes or night times, or what type of precautions our children will take?
Yeah. So lead acid batteries have been there since more than a decade. If you see in North, Banaras or Lucknow, most of these 7-seaters and two-wheelers use the lead acid batteries. But the problem with lead is toxic. Although there is a very well established recycling technology also, but second problem is it has lower energy density. As you mentioned, you have to charge it for the night, and they run it only within the city, these 7-seaters and all, or two-wheelers, so that until lunchtime they run it. Again lunch they take 2 hours or 3 hours break. Again they run it in the evening. So this is the very slow charge discharge rates and low energy density with lead acid batteries. But whereas lithium ion batteries have much higher energy density, so yeah. So you can run for more kilometers with one single charge. But both have a problem when the vehicles run in Indian roads, because they are abused, batteries are abused, because whenever you go to a bump or a speed breaker, what happens, it requires more power density. So now in our institute, we are also working on integrating supercapacitors with the batteries, so that whenever there is a high power density required, it shifts automatically. There is a BMS, battery management system, it immediately shifts to supercapacitor for few seconds. After it comes to the normal road, again batteries start working. So this integration, but for future lithium ion batteries, not even lithium ion, sodium ion. Now lithium ion will run for 2 or 3 decades, but future should be again with the sodium ion battery or lithium sulfur battery. So these will be the future technologies, and also the supercapacitor technology should come. We regularly speak to industries. The industries feel ki till now nobody is using in India supercapacitor. So someone should use it. Only then they will start thinking of taking the technology. Now see, since last 2-3 years, there is so much of rush from industry to set up lithium-ion battery plants, which was not there 2-3 years before. So that should come even regarding the supercapacitors. Then supercapacitors are useful also for these start-stop applications. Yeah.
With regard to supercapacitors, we are using redox additives, particularly in our case, we are observing more self-discharge than something.
Supercapacitors are known for self-discharge. Yes. So you have to optimize many things. The concentration of both supporting electrolyte and the redox mediator. And second thing is even the structure of your electrode matters a lot over there. Because it is redox behavior, no? Oxidation reduction. Okay? That has to be perfectly, yes, compared to batteries, supercapacitors have worse self-discharge, but you can control it by optimizing first the concentration and also what redox medium you are using. That is, for each metal, there is a particular redox medium that works well. Because I have worked with 2 or 3 types of metal oxides for pseudocapacitors. I have found that each of these I used for MnO2, Ki, but that doesn't work for nickel cobalt oxide. I had to choose something else for the nickel cobalt oxide. So the redox behavior between the electrode and electrolyte also matters a lot. So this is a 3 electrode system where you have a support third reference electrolyte. There you have just the anode and cathode. There so many things come into picture. What is the loading on the cathode? What is the loading? You don't call them cathode anode because they are both carbon. But now if you are using carbon and metal, you have a separator. What is the thickness of the separator? How much electrolyte you are filling? All these come into picture when you make a coin cell. Okay. Yeah. Yeah.
Sairam. Thank you, Dr. Sharda, for highlighting the pros and cons of various energy storage devices, the potential of combining the features of supercapacitors and batteries, role of nanomaterials in manufacturing battery materials, limitations of using lithium NMC based battery in tropical conditions, importance of using LFP based battery in India, the challenges involved in bringing science to technology, especially while scaling up the process, lithium sulfur battery as a high energy density battery with potential usage in aviation and ways to overcome its limitations, using biomass like banana plants, jute sticks, etc. for making supercapacitor materials, use of high energy density redox mediated asymmetric supercapacitors, green approach towards recycling spent lithium ion batteries and exploring anodes for sodium based battery like hard carbon. We now request our respected Department Head of Chemistry, Professor Rajni Bhandari, to offer our token of love to Dr. B. Venkat Sharada. Sairam. Thank you, ma'am. We'll now have a brief overview presentation on various area of research carried out by the faculty members at the Department of Chemistry, Sri Sathya Sai Institute of Higher Learning, presented by Dr. Swayam Siddhakar, faculty member, Department of Chemistry. Dr. Swayam.
Om Shri Sai Ram, offering myself at Bhagwan's lotus feet, esteemed speakers, guests, elders, and dear brothers and sisters. I'll be briefly touching upon the research work that as individual and as group that we are carrying out in Department of Chemistry. This will not only benefit the speakers who have come for potential collaborations and further research, plus also for students to know what kind of research is going on here, and you can explore further research and higher education with us also if you are interested in the fields. So courses offered, as you know, currently we have the BS Honors 4 years program has started. The 3 years BSc program also is running. We have the MSc program which is running only in the men's campus, and PhD is open in all the campuses. And primarily, as you can see, the basic area of work is inorganic, analytical, organic and physical chemistry. The theory papers and the research also is aimed in these fields. So we are well equipped with all the things that are needed to take a good class and do good research. So all the classrooms are equipped with the electronics, and then we have a separate organic chemistry lab, a physical chemistry lab, analytical lab. We have instrumentation lab and specialized softwares for computational courses. And additionally, with the science center, we have instruments like NMR, mass spectrometry, SEMTEM also available with us to do research. So these are the faculty members who are there currently. There are totally 14 of us, 5 madams in Anandpur campus and 9 of us here in Nilayam campus. You can see the names. I'm the youngest, so my name is on the last. So it's there. So this is the statistics about the students who are passed out of the MSc and the PhD students. As you can see, over last 5 years, 17 PhDs have been awarded, and currently around 13 PhDs are ongoing. And we have students who qualify in GATE, NET every year from the PG courses. These are some of those statistics, and also various awards like BSR fellowship, SRF from DST, CSR, all those things also have been awarded to many of our students and faculty also. Coming to the key research areas or the thrust areas, as we say, you can see it is divided into health, energy and environment. Currently, these are the 5 research problems that you are working on. That is starting with drug design, development and discovery, followed by sensing platforms, then materials for environmental remediation, novel materials for OLED and NLO, that is towards the physical chemistry and energy side, and materials for energy harvesting, storage and electrocatalysis. So under health, these are the research that are currently just started, which of course includes development of novel therapeutic agents, that is your small molecules developed for various disease targets, or we work with natural products where we extract compounds from natural products and see if they can have some medical applications. Apart from that, there are some proposed research on replacing the traditional PVC blood bags with something that is more sustainable and organic, and also to do better sensing, means identify the problems, that is a diagnostic tools, to make better diagnostic tools. So under the health section, we have Dr. Lakshminath, who is primarily working on natural products. Also, sir has good expertise on synthetic organic chemistry. and mostly all the applications are towards medicinal side. Then we have Pavana Kumari ma'am, again, synthesis of small molecules. For primarily ma'am's work is on anti-cancer drugs. Also some things like anti-inflammatory and antibacterial properties also she works on. Then this is the research that we are working on. Same under synthetic things, we have small molecule synthesis for anti-cancer, anti-inflammatory properties. And also I'm working on something which is in a fringe area of medicinal chemistry, where we try to modify the existing drug and see if we can do something better, rather than doing everything from ground up. So that is one. So under this, I have just a brief slide on this medicinal chemistry research, where we have explored over 12 plants. We have made over 400 semi-synthetic compounds. That means we have taken the natural compounds and made their derivatives. And over 800 synthetic compounds we have made, which has resulted in 3 patents, over 30 publications, and we have had 2 funded projects, and we have students who are currently working on it. And as you can see, our primary targets are anti-cancer, antibacterial, anti-inflammatory properties. And recently we have gotten into neurodegenerative diseases like your Huntington or ALS, Alzheimer's, those kind of study also we have gotten into. Under natural products, these are some of the things that we have explored. As you can see, it ranges from sponges from marine sources to mushrooms and lot of locally available medicinal plants. This is a brief list of that. The andrographilide plant is a common Ayurvedic plant which is there on the top there. Then Ganoderma mushroom, which is a good source for nutraceuticals. So all those have been studied in our department so far. So main thing, as the title says, bridging science, research and society. So as you can see, synthetic derivatives of course offers us new platform to see whether we can do better. Then followed by natural products. Natural products are the best source for home remedies, which you don't have to market also. Like you can ask people to grow the plants in their house and consume it for their own health. Drug repurposing is a new field that we are working on, where we are trying to see whether the old drugs can be reused for the new targets. So that way we avoid the cost and the time for a new drug development. And finally, pro-drugs, where we modify the drugs to see if we can increase their activity. So under this, we have done some of this work, as you can see, from Oryzilum indicum, Andrographis paniculata. So we have studied their properties. This is a detailed work on that. So the work that we have done has resulted in a patent, which is on this andrographilide molecule, various derivatives. We have taken the andrographilide molecule, modified it, made acetals, like simple organic reactions, made acetals, ketols, which you would have studied now in undergraduate program. So you can see there are 2 hydroxy groups there. So we have modified them into acetals and hemiacetals, those kind of things, or made esters out of it, and then studied, and we have found they have good anti-cancer properties. So this spiro molecules was done from ground up. Spirocyclic molecules are actually quite good therapeutic agents because they have very rigid structures. They don't change. They don't break their structure. So they had good anti-cancer properties, which also has resulted into a patent. Chalcones, I think you would have studied under your Claisen reaction, where you do chalcone molecules, and chalcones also offer a lot of biological properties. I'll just skip this. Come to the recent success story. You go back, no? Go back. Just next. Next. You're going too back. Next. Wait, before this slide, yeah. So currently under sustainability, I think you would have heard today about energy storage and materials and other things. How can you achieve sustainability in drug design and discovery? This is one of the examples. This plant, Terminalia arjuna, has a natural product called arginolic acid, which is a very good anti-diabetic and anti-cancer molecule. But the problem is when you extract from the plant, it comes as a mixture with acetic acid. So you cannot remove them conventionally. And if you want to buy arginolic acid from market, 1 mg is around 33,000. 1 milligram is around 33,000. So Lakshminath sir's group has worked on it, and they could achieve separation from 1 kg of plant material. They could get 11 gram of arginolic acid pure, which has reduced the cost considerably. So when we end up reducing cost, That also is sustainability, right? When we don't have to use extra materials and things. So it can also be sustainable. So now 11 gram is available to us at a cost at which you used to get 1 milligram. So this is one of the examples where we could achieve sustainability. Next. This is the other one which I am working on, pro drugs. Your standard, if you would have gone to any doctor, if they prescribe you diclofenac, ibuprofen, anything, they'll ask you to take antacid before, right? One antacid is given. So you take basically 2 medicines for one drug to act on you. So what we did was we found the major cause for this, NSAIDs as they're called, the painkillers. The major cause is there is a free carboxylic acid group which causes the stomach irritation and ulcers. So what we did was we just masked it with another compound which is bioactive, and then we saw the properties on the, and it has already passed the preclinicals actually. So in this we found the activity, as you can see the inflammation in mouse paw has reduced. The pain killing activity increased 50 times. Means the ibuprofen conventionally had, let's say, onset time of this much minutes. Considerably our pro drug reduced the pain killing activity, means it increased the pain killing activity considerably. And finally, as you can see the lower image, the ulceration reduced drastically. So with the slight modification by masking the carboxylic acid group in a medicine, now you don't have to take 2 medicines, you can just take 1. So there also we could achieve some bit of sustainability. Next. So these are the facilities that we have to do all this drug design and discovery, NMR, mass, FTIR, all those things are there. Next. This is one more thing which Dr. Vishweshwar is working on. These are all your handheld diagnostic tools where you can, means some things like on your neonatal, perinatal, dengue diagnosis, all those things on handheld basis, like on a phone or in a small device they can carry out. Currently their aim is to club all of these separate devices and give you one single point of care device so that you can, it can be run in mobile hospitals and so forth. Coming to energy, of course, under energy we have this work which is going on, energy efficient OLEDs, and then materials for energy storage and applications, and hydrogen storage materials, all those things. In this, Ravi Kishore sir is primarily, he works on modeling the problem first theoretically and then try and work it out experimentally. So sir is currently working on the OLEDs that you have seen so far, OLEDs. So sir is currently working on it. Next. Pratyusha ma'am is working on bio-inspired molecules for absorption and desalination and hydrogen storage. Of course, again, she also tries to model it theoretically and then do the experimental work on it. Shantanu sir, he works on bioactive materials, like some of these which can be used even as bone replacement and those kind of things. So you can see the details there. Next. Our J.K. Kiran sir is primarily working on electrocatalysis, and his paper, one of the papers was published in Nano Energy, which is 17 impact factor, and it primarily talks about gold nanoparticles, which is basically for green synthesis of gold nanoparticles. The work abstract is present here. Next. And coming to Dr. Sai Smaran, he works on energy storage and electrocatalysis. Next slide. So these are some of the works, the research work that he has taken up. That is your supercapacitors and other electrocatalysis reactions. Next. And finally, coming to environment, mostly majority of our work, including Dr. Ganesh here and our HOD ma'am, they all work on defluoridation or water purification. The biggest problem in this area is fluoride contamination in our Puttaparthi and Rayalaseema area, and getting clean drinking water is one of the aim. That also Swami also had pursued that. So under the same scope, many of the teachers are working on domestic fluoride water filters and all those kind of things. Also, other teachers are working on different materials that can be substituted for the conventional materials, like biodegradable materials. So we have our HOD ma'am, Rajni Bhandari ma'am, who is working on the water purification. Next. Sunil sir, he's working on materials which can have bioremediation property. You can also use them for drug delivery, mostly on the sustainable materials, which are cost effective and more biocompatible. Then Prafulla Chandra sir, he is working on this atmospheric pollutants, that is your microplastic and PM 2.5 pollutants, using our mass spec instrument which is there. So he's working on air pollution basically. And Raji ma'am is also working on materials and composites that can be used for environmental remediation and other biomedical applications. So finally, coming to some of the milestones that we have, if you see over the last 10 years, our research output has increased, and we have had almost 114 publications in last 5 years, and many of the work has also featured in journal cover pages. And the highest being at 16.3, as I was telling, J.K. Kiran sir's paper, and many of these papers, average impact factor, as you can see, is quite high. So some of the patents that have come in last 5 years, and another 2 I have not added, which is from Dr. Vishweshar's side, but these are, we have overall 7 patents as of now. And to tell you, Institute's first patent, which was like, which the trust allowed us to patent, was from the Department of Chemistry. The first 2 patents had come from Department of Chemistry. So that is there. Next. And these are the funded projects. We have got various funding for many of these applications which we have proposed to both private and government bodies. This is just a small highlight which the team from the Star Lab, as they call themselves, had achieved, where they could develop a very cost-effective COVID detection kit that time. Of course, now it is not needed, but at the time when it was needed, they could come up at a very fast, almost within 4 minutes, it could give the result. And we were the only institute, academic institute, to get a permission to run this COVID diagnostic kit. So these are some of the collaborations that we have, international collaborations and national collaborations. Next. We have quite a few alumni who work on very prestigious organizations. You can see the names, means abroad and in India. And of course, now this is the path forward where we want to work with industries and other collaborators, so we can carry our research forward in a meaningful way and really achieve that bridge between research and society. Thank you for your patient listening. Sai Ram.
Sai Ram. Thank you, Dr. Swayam, for presenting an overview of our research activities in the Department of Chemistry. With this, we conclude the day 1 of the International Symposium on Chemistry for Sustainable Future, Bridging Science and Society. We'll be assembling back here tomorrow morning at 8:45 a.m. for the day 2 proceedings of the symposium. Now, we request our distinguished invited speakers, senior professors, faculty members, and students to assemble near the auditorium alley for a photograph session, which will be followed by a tea break before we proceed to Mandir for darshan. Sai Ram.